In the year 1610, a visionary gazed through a crude lens and saw not the majestic, iconic rings we celebrate today, but a bewildering anomaly. This was Galileo Galilei, the pioneering Italian astronomer, and his initial encounter with Saturn was not one of awestruck clarity, but of profound, unsettling confusion. His early sketches, stark and raw, reveal a planet not encircled by a graceful halo, but rather flanked by two bizarre, ear-like appendages, or perhaps companion spheres, clinging stubbornly to its sides. This was the first hint of Saturn's true nature, yet it was a clue so distorted, so alien to anything seen before, that it plunged the scientific world into nearly 50 years of bewildered speculation. Galileo's primitive telescope, though revolutionary for its time, possessed significant limitations. It offered an imperfect, fuzzy glimpse of the cosmos, much like trying to discern intricate details through a frosted window or an out-of-focus photograph. What Galileo saw was the outermost edges of Saturn's rings, just barely resolved, appearing as two distinct bulbous protrusions. His mind, desperately trying to make sense of incomplete and ambiguous data, sought familiar patterns. This innate human tendency to interpret the unknown through the lens of the known led him to describe these spectral companions as handles or ears, anchoring his observations in a tangible reality, even if it defied all known celestial mechanics. The mystery deepened dramatically when these strange ears seemed to vanish entirely, only to reappear years later, a cosmic disappearing act that deeply troubled the Italian astronomer. Imagine the frustration, the scientific torment of observing a celestial body fundamentally change its appearance, then revert. Was it an optical illusion, a trick of light? Or was the universe playing a cruel, inexplicable game with the very fabric of reality? This wasn't merely a simple mistake. It was a foundational enigma in early telescopic astronomy that fueled intense debates and sparked wild theories across Europe, each more fantastical than the last, as scholars grappled with the implications of a planet that seemingly shapeshifted before their very eyes. It would take nearly half a century for this profound celestial riddle to find its first solution. In the year 1655, a brilliant Dutch scientist, Christian Huygens, turned his own vastly superior telescope towards the distant, enigmatic planet. Huygens' instrument, a monumental leap forward in optical design, offered unprecedented clarity, revealing details that had been utterly obscured to Galileo. With this clearer view, Huygens was able to correctly hypothesize the existence of a thin, flat ring, nowhere touching the planet itself, a revolutionary idea that completely redefined our understanding of Saturn. He proposed a structure that was not solid and attached, but a distinct, ethereal band encircling the world. Huygens' breakthrough was not solely a testament to his superior technology. It was equally a triumph of abstract reasoning and elegant geometrical thinking over direct, flawed observation. Where Galileo saw two discrete objects, Huygens deduced a continuous, planar structure. He didn't just see better, he thought better, applying rigorous mathematical principles to interpret what his improved optics revealed. This moment solidified a central theme that would echo throughout centuries of Saturnian exploration. Our understanding of this ringed giant has always been a mirror, reflecting both the limits and the advancements of our own technology, and more importantly, the boundless expanse of our human imagination. Saturn is a cosmic puzzle that reveals as much about us, the observers, as it does about the planet itself. The historical documents and letters from that era provide a fascinating glimpse into the intellectual ferment ignited by this initial enigma. They show how Galileo's bewildering observation, far from being a dead end, paradoxically set the stage for centuries of scientific fascination. It propelled the urgent development of more powerful observational tools, pushing the boundaries of lens grinding and optical design. What began as a puzzling planetary oddity, a source of confusion and debate, was slowly, deliberately, transformed into the iconic celestial marvel of our solar system. This historical deep dive provides the essential context, framing the entire story of Saturn not as a static collection of facts to be memorized, but as an unfolding, dynamic investigation, driven relentlessly by human curiosity and ingenuity, a journey that continues to this very day. For centuries, the iconic rings of Saturn have captivated humanity, their ethereal beauty an assumed symbol of cosmic permanence. They have been viewed as an ancient, immutable halo, dating back to the very dawn of our solar system. Yet, what if this perception, deeply ingrained in our collective imagination, is profoundly mistaken? What if this fleeting masterpiece is not an eternal monument, but a cosmic mayfly, whose spectacular, delicate existence is merely a brief, precious moment in the vast stretches of cosmic time? This astonishing revelation comes not from distant speculation, but from the most intimate encounter we have ever had with the ringed giant. The year was 2017, and NASA's Cassini mission, after 13 years orbiting Saturn, was approaching its dramatic grand finale. In a breathtaking act of scientific audacity, the spacecraft was commanded to perform a series of 22 daring dives, plunging directly into the uncharted abyss between Saturn and its innermost rings. This was more than just a spectacular conclusion. It was an unprecedented opportunity to gather data from a region no probe had ever dared to enter, a final, courageous quest to unlock the planet's deepest secrets. Deep within Cassini's scientific payload was a marvel of engineering, the Ion and Neutral Mass Spectrometer, or INMS. As the probe executed its perilous dives, this instrument acted as a cosmic sniffer, directly measuring the influx of material falling from the rings into Saturn's upper atmosphere. What it detected was a continuous, steady drizzle of microscopic particles, a phenomenon scientists have aptly dubbed ring rain. This was not just a theoretical concept, it was a tangible, measurable process, observed as Cassini pierced the veil between ring and planet. But how, precisely, does this rain of icy dust occur? It is a complex dance between light, particles, and magnetism. The microscopic particles that compose Saturn's rings, mostly water ice, are constantly bombarded by ultraviolet light from the sun and by micrometeoroid impacts. These interactions can strip electrons from the ring particles, giving them an electrical charge. Once charged, these tiny fragments become susceptible to Saturn's powerful magnetic field. Like iron filings drawn to a magnet, these charged particles are pulled along the planet's invisible magnetic field lines, funneling them inexorably towards Saturn's upper atmosphere, where they are ultimately deposited, slowly but surely raining down onto the gas giant. The implications of this continuous downpour are nothing short of mind-bending. Scientists, including James O'Donoghue, a planetary scientist from NASA's Goddard Space Flight Center, meticulously analyzed the INMS data. Their calculations painted a startling picture of decay. The rings are losing mass at a dramatic, almost unfathomable rate. To put this into perspective, the sheer volume of material draining into Saturn's atmosphere is enough to fill an Olympic-sized swimming pool every single half hour. That is a staggering 24 Olympic pools every day, or over 8,700 Olympic pools in a single year. This astonishing rate of depletion leads to a truly profound conclusion. Saturn's rings are not primordial. They are not billions of years old, coexisting with the planet since its formation. Instead, they are a relatively recent addition to the Saturnian system, perhaps only 10 million to 100 million years old. Let that sink in for a moment. This means that the magnificent rings we observe today likely formed during a period when dinosaurs still roamed the Earth, a cosmic coincidence that redefines our understanding of planetary evolution. What we are witnessing is not an ancient relic, but a comparatively young, dynamic structure. If the rings are not primordial, then where did they come from? The leading hypothesis suggests a cataclysmic event, perhaps the destruction of a large icy moon that strayed too close to Saturn's gravitational clutches. As this unfortunate moon ventured within what is known as the Roche's limit, the minimum distance a satellite can orbit a celestial body without being torn apart by tidal forces, Saturn's immense gravity would have ripped it to shreds. The shattered fragments would then have spread out, gradually forming the majestic, yet ultimately transient, ring system we see today. It is a story not of static creation, but of violent, recent genesis. This revelation transforms our appreciation of Saturn's rings. They are no longer merely a beautiful, passive object of study, but a dynamic, ephemeral structure. They are a cosmic mayfly, a fleeting masterpiece whose spectacular beauty we are incredibly fortunate to witness in our brief moment of cosmic time. This understanding imbues our study of this celestial wonder with a new layer of urgency and preciousness. It emphasizes that what we observe through our telescopes, what Cassini revealed in its final, courageous dives, is merely a snapshot in a constantly evolving, living story, a story that continues to unfold with every passing second. The cosmic drama of Saturn's rings is a spectacle of unparalleled beauty, a shimmering disk that defines the very image of a gas giant. Yet, to see them merely as a static, passive object of beauty is to miss their most profound secret. These are not just frozen shards of ice gracefully orbiting their parent world. No, Saturn's rings are a vibrant, dynamic arena where invisible forces constantly reshape the landscape, a cosmic ballet choreographed by an unlikely cast of characters, its tiny, inner moons. These are not merely satellites. They are the gravitational choreographers, endlessly sculpting, shaping, and influencing the very structure of the rings in a complex, interconnected dance. Consider the moon Pan, a diminutive world just 28 kilometers across, a size barely larger than a major metropolitan city. This is no ordinary satellite. Pan orbits deep within the Inca Gap, a prominent division in Saturn's A ring, a seemingly impossible void in the sea of icy particles. How does this minuscule moon maintain such a vast, clear lane? Pan acts as a cosmic snowplow, its gravity ceaselessly clearing its orbital path. As it sweeps through the ring plane, its gravitational tugs perturb particles on either side, shunting them out of its way. The stunning images captured by the Cassini spacecraft reveal the undeniable evidence: scalloped edges along the gap, where the ring particles are pushed and pulled into intricate patterns. These are not just minor ripples, they are vertical waves, towering structures within the thin ring plane, sometimes tens of meters high. To grasp the scale, understand that these disturbances, these wakes, carved by Pan, can extend for hundreds of kilometers along the ring, structures profoundly larger in extent than the Moon itself. It is like a minuscule pebble creating ripples that span an entire lake. Even more remarkable is Daphnis, a moonlet smaller still than Pan, measuring a mere 8 kilometers across. This tiny world resides within the narrower Keeler Gap, where it creates some of the most breathtaking visual phenomena in the entire Saturnian system. As Daphnis orbits, its gravity creates spectacular wave-like structures both above and below the ring plane. These waves, captured in exquisite detail by Cassini, resemble the bow waves of a ship moving through water. Except here, the water is made of billions of icy particles, each jostled into a precise, undulating pattern by the gravitational whispers of this minuscule moon. These waves can reach heights of nearly 2 kilometers, an astounding feat for such a small celestial body, demonstrating the profound and far-reaching influence that even the smallest objects exert within this gravitational system. This is direct observation of celestial mechanics in action, showing how minute gravitational forces can orchestrate grand designs. But the sculpting power of moons extends far beyond direct clearing. Some of the most dramatic features in the rings, like the vast Cassini division, a gap spanning nearly 5,000 kilometers, are born from a more subtle, yet equally powerful phenomenon: orbital resonance. Think of it like this: if you push a child on a swing, a small push at just the right moment in their swing's arc can build up into a much larger swing over time. Similarly, Mimas, one of Saturn's larger, more distant moons, exerts a gravitational pull on ring particles. When ring particles orbit at a rate that is a simple fraction of Mimas's orbital period, for instance, completing exactly 2 orbits for every 1 orbit of Mimas, they experience a repetitive, synchronized tug. These repeated gravitational nudges, though individually weak, accumulate over countless orbits, gradually clearing out vast swaths of ring material. This resonant interaction acts as a cosmic broom, sweeping the particles out of specific orbital pathways and creating the wide, seemingly empty expanse of the Cassini division, a testament to the elegant, predictable power of celestial mechanics. The rings are also a laboratory for the earliest stages of moon formation, a process happening before our very eyes. Scattered throughout the rings are intriguing propellers, small, propeller-shaped disturbances in the ring material. These are not gaps cleared by known moons, but rather telltale signs of unseen moonlets, clumps of ice and dust typically ranging from a few tens of meters to a few hundred meters in size, still embedded within the rings themselves. The gravitational perturbations from these nascent moonlets carve out distinct, localized clearings, leaving behind patterns reminiscent of a propeller blade. These ephemeral structures offer a glimpse into the dynamic, ongoing process of accretion and formation, suggesting that the rings are not a static collection of debris, but a place where new, small worlds might be continuously attempting to coalesce, perhaps even evolving into larger moons over eons. This intricate interplay of gravity and matter transforms our understanding of Saturn's rings entirely. They are not merely a uniform sheet of ice, but a living, breathing laboratory for celestial mechanics. Here, we can directly observe the fundamental forces that shaped our entire solar system in its infancy, from the gentle shepherding of tiny moonlets to the grand, resonant clearing of vast divisions. By focusing on these gravitational choreographers, we shift our perspective from a passive appreciation of beauty to an active engagement with the cosmic ballet of physics, a performance unfolding across billions of kilometers, driven by forces we are only just beginning to truly comprehend. When we consider Saturn's celestial ballet, our focus often falls upon the grand, shimmering rings or their tiny, intricate choreographers, the moons that sculpt their every arc and division. Yet, deep within that breathtaking system, a hidden engine of creation pulses, a tiny moon actively reshaping its entire environment, not merely reacting to it. This is the story of Enceladus, a world less than 500 kilometers across, a cosmic pearl whose frigid exterior belies a heart of saltwater and an astonishing geological engine within. For decades, Enceladus was just another icy dot among Saturn's 62 known satellites, a seemingly inert sphere adrift in the outer solar system's perpetual twilight. But in the year 2005, the Cassini spacecraft, a silent sentinel orbiting the ringed giant, made a discovery that shattered our preconceived notions of where life's ingredients might thrive and how planetary bodies truly behave. It observed enormous plumes of water ice and vapor erupting violently from the Moon's south polar region, specifically from 4 prominent fissures nicknamed tiger stripes. This was not some ancient, dormant process, but a dynamic, ongoing spectacle, jets of material blasting hundreds of kilometers into space, a cosmic geyser rivaling Earth's most powerful volcanic eruptions. The sheer existence of these geysers was paradigm-shifting, yet the true revelation lay in their chemical composition. Cassini wasn't merely a camera, it was a sophisticated scientific laboratory. Its Cosmic Dust Analyzer, or CDA, acted as an interstellar forensic tool, flying directly through these icy plumes, scooping up particles and analyzing their contents. What it found was a chemical signature that sent ripples of excitement through the scientific community. The plumes were rich not only in water ice, but also in salts, indicating a substantial liquid water ocean beneath Enceladus's icy crust. More astonishingly, the CDA detected complex macromolecular organic compounds, the very building blocks of life as we know it. This wasn't just water. This was a chemical soup, hinting at an environment ripe with potential. The immediate question became, what powers this incredible activity? How could such a small, distant moon maintain a vast liquid ocean and power these continuous eruptions? The leading hypothesis centers on a remarkable geochemical process known as serpentinization. Deep beneath Enceladus's icy shell, at the boundary where its rocky core meets its immense subsurface ocean, water reacts with warm rock, specifically with iron-rich minerals. This chemical reaction, a natural phenomenon, releases heat and, crucially, produces hydrogen gas. It is a process analogous to the hydrothermal vents found deep in Earth's oceans, such as the Lost City Field in the Atlantic, where life thrives in absolute darkness, fueled not by sunlight, but by the chemical energy derived from these rock-water interactions. On Enceladus, this hydrogen gas could provide a potent source of chemical energy for potential microbial life, acting as a crucial food source in a sunless world. But the story of Enceladus's plumes is not solely one of potential habitability or internal geology. It is also a tale of cosmic creation on a truly grand scale. The material ejected from these plumes does not simply fall back to the Moon's surface. Instead, a significant portion escapes Enceladus's weak gravity, dispersing into space around Saturn. And here lies a key connection, a profound link that transforms our understanding of the entire Saturnian system. This continuous outpouring of water ice and organic compounds is the primary source for Saturn's entire E-ring. This E-ring, the outermost of Saturn's broad, diffuse rings, is not a remnant of ancient cosmic debris. It is actively, continuously being built by the very Moon embedded within it. To fully grasp the magnitude of this, consider that Enceladus is a tiny sphere, just 500 kilometers in diameter, roughly the distance from New York City to the Canadian border, or from London to Paris. Yet, this diminutive world is single-handedly constructing one of the largest structures in the entire solar system, a vast, luminous ring of icy particles spanning hundreds of thousands of kilometers. It is a story not just of discovery, but of active, ongoing creation, a testament to the dynamic forces at play within Saturn's domain. The pioneering work of scientists like Caroline Porco, the formidable Cassini imaging team lead, was crucial in directing the spacecraft to perform the daring maneuvers necessary to fly directly through these plumes. Her persistent advocacy transformed our understanding of ocean worlds, proving that hidden oceans, bubbling with the potential for life, could exist far beyond the familiar bounds of Earth. 54 years after the first human stepped onto the lunar surface, and 2 years before Cassini's dramatic plunge into Saturn's rings, humanity achieved another extraordinary feat, a landing on a world shrouded in perpetual haze, an event that reshaped our understanding of what a habitable planet might truly look like. This was not Earth, but Titan, Saturn's largest moon, a colossal world, larger than the planet Mercury, locked in a deep freeze, yet paradoxically, the most compelling analog for our own planet in its primordial youth. Its thick orange atmosphere, opaque to visible light, had for centuries hidden its surface, sparking endless speculation. Long before direct observation, a visionary intellect pondered this veiled moon. In the 1980s, the legendary astronomer Carl Sagan, with an almost prophetic foresight, theorized that Titan's nitrogen-rich and methane-laden atmosphere was not merely a passive blanket, but an active chemical factory. He proposed that ultraviolet light from the sun, tirelessly interacting with these atmospheric gases, would trigger complex reactions, generating a constant rain of organic molecules he famously termed tholins. These sticky, tar-like substances, distinct from any living matter, were, in Sagan's view, the very chemical precursors to life, falling ceaselessly onto Titan's surface, awaiting a catalyst. The true unveiling of Titan began in earnest on January 14, 2005. On that day, the European Space Agency's Huygens probe, a hardy robotic explorer designed to withstand the Moon's cryogenic temperatures and dense atmosphere, began its dramatic descent. This wasn't merely a landing, it was an immersion into an alien sensory landscape, meticulously recorded for humanity. As Huygens pierced the thick clouds, its cameras revealed an astonishing vista. Dendritic river channels, strikingly similar in form to those carved by water on Earth, snaking across the frigid surface. The probe's microphones captured the eerie, whisper-like sound of the wind, a chilling testament to an active atmosphere. And then, with a distinct and satisfying thud, it touched down, landing on a surface described by the mission scientists as having the consistency of damp sand, littered with pebbles of water ice. This monumental landing, combined with the relentless radar mapping performed by its parent spacecraft, NASA's Cassini orbiter, provided the definitive ground truth that unveiled Titan's true nature. The combined data confirmed something truly extraordinary. Titan boasts a complete methanological cycle, a precise parallel to Earth's familiar hydrological cycle. Instead of water, it is liquid methane and ethane that flow, rain, and evaporate. Methane rain precipitates from the clouds, feeding rivers that carve channels into the icy crust, ultimately emptying into vast lakes and seas, some stretching hundreds of kilometers across, filled with hydrocarbon liquids. It is a world where clouds drift and precipitation falls, forming landscapes that eerily mirror our own, yet under conditions that would instantly freeze any life form from Earth. The core fascination of Titan, however, lies in the complex organic chemistry that unfolds across its entire sphere. Here, at a frigid average surface temperature of approximately -179 degrees Celsius, a temperature at which water ice becomes rock hard, the fundamental building blocks of life are forming in abundance. Ultraviolet radiation from the sun, cosmic rays, and even the internal heat of the moon drive intricate chemical reactions within its atmosphere and on its surface. Nitrogen and methane combine to create a vast array of hydrocarbons and nitriles, molecules like acetylene and hydrogen cyanide, compounds universally considered essential for the spontaneous generation of amino acids and nucleic acids, the very foundation of life. This makes Titan a natural planetary-scale laboratory, demonstrating how the raw materials for life can arise in extreme non-biological environments. Yet a tantalizing possibility exists beneath this frozen, chemically active surface. Scientific models and gravitational measurements suggest the strong likelihood of a vast subsurface liquid water ocean, a hidden sea sandwiched between Titan's rigid icy crust and its rocky core. This liquid water, warmed by the radioactive decay within the Moon's interior, represents a potential habitable zone in an otherwise intensely cold environment. This scenario presents a profound astrobiological puzzle. Could the complex organic molecules forming on the surface, those tholins and other hydrocarbons, eventually find their way down to this subsurface ocean? And if they do, could the presence of liquid water, even far from sunlight, spark the next, more advanced stage of chemical evolution, perhaps leading to biotic chemistry or even rudimentary forms of life? This two-tiered system transforms Titan into an unparalleled laboratory for understanding the very origins of life. The surface offers a unique window into prebiotic chemistry, showcasing how life's fundamental building blocks can spontaneously form under conditions vastly different from early Earth, yet still rich in the necessary chemical ingredients. Meanwhile, the potential subsurface ocean offers a tantalizing environment for the next crucial step, the mixing of these organics with liquid water, providing the solvent and medium necessary for complex molecular interactions. It is a world that compels us to reevaluate our definitions of habitability, pushing the boundaries of where and how life might emerge in the cosmos. For all its visible grandeur, the majestic, sweeping expanse of its rings, the intricate dance of its ice-sculpted moons, Saturn conceals another, equally profound dimension. This realm is invisible to the naked eye, a vast, dynamic arena of unseen forces, where the planet itself sings a cosmic symphony on wavelengths we cannot perceive. It is here, within Saturn's powerful magnetosphere and its eerie radio emissions, that we uncover the planet's hidden voice, a language spoken in crackles, whistles, and hisses. The discovery of this invisible chorus dates back to the year 1980, when the Voyager 1 spacecraft, on its daring journey through the outer solar system, first detected a powerful form of intense radio wave emanating from the ringed giant. Scientists named it Saturn kilometric radiation, or SKR. This radiation, utterly undetectable to the human ear without the aid of specialized instruments, was captured by radio antennas aboard the probe, revealing a constant, fluctuating signal. It was, in essence, the very voice of the planet, a direct product of the ceaseless interaction between the Sun's relentless solar wind and Saturn's immense, complex magnetic field. To truly grasp the alien beauty of this phenomenon, we must transcend our ordinary senses. Scientists have employed a technique known as data sonification, translating the raw SKR signals into auditory experiences. When listening to these transformed frequencies, a symphony of the unseen unfolds. Sharp crackles, ethereal whistles, and a pervasive, almost unsettling hiss. This is not just abstract data. It is a visceral experience of complex plasma physics, rendered audible, offering a direct window into the dynamic, chaotic ballet of charged particles millions of kilometers away. But how are these powerful emissions generated? The mechanism is a breathtaking cosmic ballet of energy and magnetism. Energetic electrons, accelerated to incredible speeds by the powerful forces within Saturn's magnetosphere, are compelled to spiral along the planet's magnetic field lines. As these particles plunge towards the planet's poles, they collide with atoms and molecules in the upper atmosphere, exciting them and causing them to glow. This process creates the spectacular ultraviolet auroras that shimmer high above Saturn's poles, much like Earth's own northern and southern lights. Observatories like the Cassini probe and the venerable Hubble Space Telescope have provided us with breathtaking visualizations of these light shows, revealing intricate, shifting patterns of energy that paint the polar skies in a palette of invisible hues. Beyond their mesmerizing beauty, these strange signals hold profound scientific secrets. One of the most perplexing mysteries for planetary scientists for decades was determining the true rotation rate of Saturn's interior. Unlike Earth, Saturn is a gas giant. It has no solid surface to track, no fixed landmark to observe as it spins. This made pinpointing its internal rotation incredibly difficult. Yet, the periodic fluctuations and rhythmic patterns embedded within the Saturn kilometric radiation provided a key. By meticulously analyzing the SKR, scientists could effectively listen to the planet's deep internal rhythm, unlocking the precise speed at which its vast gaseous core turns, a remarkable feat of cosmic eavesdropping. And what feeds part of this dynamic symphony? A surprising contributor, one we have explored before, the tiny moon Enceladus. We have seen how this diminutive world, barely 500 kilometers across, continuously blasts enormous plumes of water ice and vapor into space from its south polar region. These geysers do more than just create a diffuse ring around Saturn. They also inject a steady stream of charged particles directly into Saturn's magnetic environment. This constant loading of the magnetosphere directly influences its auroral activity, intensifying the ultraviolet light shows at the poles and subtly altering the very radio emissions we detect. This connection reveals a truly profound truth. The Saturnian system is far more than just a collection of solid bodies and rings. It is an invisible, dynamic, and interconnected network of magnetic fields and energetic particles, where the internal geological activity of a tiny moon can reverberate across hundreds of thousands of kilometers, influencing the vast planetary-scale orchestra of the auroral hiss. It is a cosmic symphony playing out on a scale that defies our everyday understanding, a testament to the unseen forces that sculpt and define worlds. For centuries, our telescopes have peered into the solar system, revealing worlds of ice and fire, gas giants adorned with rings, and moons shrouded in mystery. We have sent robotic envoys to orbit and to land, gleaning precious data from across the vast cosmic ocean. But what if the next great leap in exploration isn't about reaching a new world, but truly living on one, however briefly, exploring it not just from orbit or a fixed landing spot, but with the freedom of flight? This is the audacious vision behind Dragonfly, humanity's most ambitious expedition yet to Titan, Saturn's largest and most enigmatic moon, a world that holds secrets to our own planetary origins. Dragonfly is not a traditional rover designed to crawl across a surface, nor is it merely an orbiter observing from afar. This is a nuclear-powered, car-sized quadcopter drone, an 8-bladed rotorcraft built to soar through Titan's thick, nitrogen-rich atmosphere, which is 4 times denser than Earth's. This unique design liberates us from the confines of a single landing site, allowing for unprecedented mobility across a landscape eerily reminiscent of a frozen, primordial Earth. Its primary objectives are nothing less than to characterize Titan's habitability and to delve deep into the progression of its complex prebiotic chemistry, seeking answers to how the very building blocks of life first assembled. The journey of Dragonfly will begin with a carefully chosen landing site, the Selk crater region. This location was selected not by chance, but for its rich geological tapestry. It is an impact basin, a scar left by a cosmic collision that excavated a unique mixture of water ice and complex organic materials from beneath the moon's surface, exposing them for Dragonfly to sample. Scientists believe that the warmth generated by this ancient impact could have briefly melted subsurface ice, creating a transient liquid water environment where these organic molecules might have interacted, offering a window into the initial conditions necessary for life's emergence. It is a natural laboratory, waiting to reveal its secrets. One of the most remarkable aspects of Dragonfly is its revolutionary mobility. Unlike Mars rovers that traverse meters per day, this drone will be able to perform multiple leaps, each covering several kilometers, easily soaring over dunes, rivers, and rugged terrain that would be impassable for wheeled vehicles. After each flight, Dragonfly will settle down at its new location, spending one full Titan day, a staggering 16 Earth days, conducting a suite of experiments before lifting off for its next destination. This patient, methodical approach allows for in-depth analysis at diverse geological sites, painting a comprehensive picture of Titan's chemical and geological diversity. At the heart of Dragonfly's scientific arsenal is the DRAMIS, the Dragonfly Mass Spectrometer. This cutting-edge instrument is designed to drill into Titan's surface, extracting samples of the organic materials that coat this frigid world. Once collected, DRAMIS will then analyze their precise chemical composition with unprecedented precision, seeking signatures of prebiotic processes, perhaps even the faint echoes of biological activity, if it ever existed. This is a cosmic detective story, with Dragonfly as the forensic specialist, painstakingly sifting through the evidence frozen in time. The excitement surrounding this mission is palpable, shared by a dedicated team of scientists and engineers. Dr. Elizabeth Zibby Turtle, the mission's principal investigator from the Johns Hopkins Applied Physics Laboratory, encapsulates this enthusiasm. She speaks of Dragonfly not just as a machine, but as a pathfinder, a visionary tool that will push the boundaries of what we thought possible in planetary exploration. It is a mission built on decades of remote observation by spacecraft like Cassini and the brief but pivotal touchdown of the Huygens probe. Dragonfly represents the next logical, monumental step, a long-term, mobile, in-situ laboratory, capable of exploring vast tracts of an alien world in ways we've only dreamed of until now. This pioneering mission makes the future of planetary exploration tangible, igniting our imaginations with the prospect of truly understanding worlds beyond our own. It charts a direct path to answering the profound questions that have long lingered about Titan's potential as a cradle for life's precursors, moving beyond theoretical models to direct, on-site investigation. Dragonfly is poised to rewrite our understanding of how life might begin, not just on Earth, but across the vast, unexplored reaches of the cosmos. Could the most profound insights into our own existence, into the very origins of life and the unfolding drama of planetary evolution, lie not buried beneath our feet, but suspended millions of kilometers away, within the shimmering embrace of a distant ringed world? Our long journey to Saturn has been more than a grand tour of a celestial Titan and its magnificent entourage. It has been an expedition into the fundamental forces that shape the cosmos, a quest that consistently challenges our assumptions and expands the very limits of our cosmic perspective. We have witnessed the astonishing revelation that Saturn's iconic rings, once believed to be as ancient as the planet itself, are in fact a fleeting masterpiece, perhaps a mere 100 million years old. This ephemeral, youthful nature of the rings forces us to reconsider the timeline of our solar system, suggesting a far more dynamic and recent history for some of its most prominent features. It is a reminder that even the grandest cosmic structures can be transient, like cosmic mayflies, whose spectacular beauty we are incredibly fortunate to witness in our brief moment of cosmic time. This understanding shifts our perspective from a static universe to one of constant flux and unexpected, dramatic events. Deep within that luminous disk, we observed an intricate gravitational ballet, a cosmic choreography performed by Saturn's tiny inner moons. These diminutive worlds, like Pan, a mere 28 kilometers across, or Daphnis, just 8 kilometers, are not passive observers. They are the gravitational choreographers, endlessly sculpting, shaping, and influencing the very structure of the rings in a complex, interconnected dance. The scalloped edges, the towering waves, the vast divisions carved by orbital resonance, all serve as a living microcosm of planetary formation itself. Here, writ large across hundreds of thousands of kilometers, we can directly observe the fundamental forces that shaped our entire solar system in its infancy, a testament to the elegant, predictable power of celestial mechanics. Then there is Enceladus, a world that utterly transformed our definition of where life might thrive. This tiny moon, barely 500 kilometers in diameter, once considered an inert sphere, pulses with a saltwater heart. Enormous plumes of water ice and vapor, blasting hundreds of kilometers into space from its south polar tiger stripes, contain not only water and salts, but complex macromolecular organic compounds. Powered by the geochemical process of serpentinization occurring at the boundary between its rocky core and vast subsurface ocean, Enceladus is an active, life-supporting engine, proving that habitability can exist in the most unexpected of places, fueled by chemical energy rather than sunlight. And in a profound twist, this diminutive world actively builds one of the largest structures in the solar system, its ejected material forming Saturn's entire diffuse E-ring, making it a story of creation, not just discovery. And who can forget Titan, Saturn's colossal moon, larger than the planet Mercury? Shrouded in a thick orange haze, it revealed itself as a frozen prebiotic laboratory, a world where liquid methane and ethane flow in rivers, collect in lakes, and fall as rain, mimicking Earth's water cycle. At a frigid -179 degrees Celsius, the fundamental building blocks of life are forming in abundance, driven by the ceaseless interaction of nitrogen and methane. This world offers a tangible glimpse into Earth's own chemical past, showing how the raw materials for life can arise in extreme, non-biological environments. The tantalizing possibility of a subsurface liquid water ocean, a hidden, habitable zone beneath its icy crust, further compels us to consider Titan as a two-tiered laboratory, demonstrating the steps that can lead from non-living matter to life itself. Binding this entire magnificent system together is an invisible magnetic symphony, an eerie chorus of crackles, whistles, and hisses emanating from Saturn's powerful magnetosphere. This Saturn kilometric radiation, undetectable to the human ear without specialized instruments, is the planet's very voice, a direct product of the ceaseless interaction between the solar wind and Saturn's immense magnetic field. By listening to this cosmic music, scientists could determine the true rotation rate of Saturn's gaseous interior, a problem that had baffled them for decades. Furthermore, the volcanic plumes of Enceladus load this very magnetic environment with charged particles, directly influencing its auroral activity and radio emissions, revealing an interconnected network where the geological activity of a tiny moon can resonate across hundreds of thousands of kilometers, shaping the planetary-scale orchestra of the auroral hiss. Saturn, then, is not merely a planet with moons and rings, it is a system of systems, a nested set of complex interacting environments that serves as an unparalleled natural laboratory. It teaches us about geology on icy worlds, the intricate chemistry of prebiotic compounds, the fundamental physics of gravitational interactions and magnetic fields, and perhaps most profoundly, the vast, unexplored possibilities of astrobiology all at once. Our initial confusion, born from Galileo Galilei's first blurry observations in 1610, where the rings appeared as bizarre ears, to the breathtaking, revelatory plunge of the Cassini spacecraft in 2017, Saturn has consistently defied our expectations and pushed the boundaries of human inquiry. This distant world refuses to offer definitive answers, but instead poses even deeper questions for our future. How common are such dynamic systems in the galaxy, systems where active geology, complex chemistry, and intricate gravitational dances unfold simultaneously? Does the astounding presence of both a frozen prebiotic world like Titan and a potentially habitable ocean world like Enceladus within a single planetary system suggest that the ingredients for life, and perhaps life itself, are far more widespread than we once dared to imagine? By diligently studying the intricate workings of the Saturnian system, we are not just observing a faraway planet. We are ultimately piecing together the grand unfolding story of planetary evolution itself, a story that provides crucial context for understanding our own origins, our tenuous place in the vast cosmic web, and the profound, lonely beauty of our precious existence within the universe.